Okay, so let's talk about polarity. We've talked about polarity in chapter 4. Remember we said polarity was a difference in electronegativity. Remember we introduced electronegativity and said that was the ability of an atom to draw an electron to itself within a bond. And every element on the periodic table is given a value of electronegativity. And if the difference of the electronegativity is between 0.4 and 2, we say that that is a polar covalent bond. So this was talking about bonds that are polar or non-polar. Now we're going to talk about polarity as it applies to the whole molecule. So this is a little bit different. So what we said before about bond polarity, bond polarity is a separation of charge based on different electronegativities of atoms in a covalent bond. So that's what we said in chapter 4 about polarities. So now we are talking about molecule polarity. So the molecular polarity has to do with the sum of all the polarities of the individual bonds, including the strength of the bonds and the orientations. Okay, so what does that mean? So let's look at an example. So let's look at a molecule. For example, let's look at the electronegativity difference of carbon and hydrogen. Okay, so this says that the electronegativity of hydrogen is about 2.3 and carbon is about 2. I can't see that. Hang on just a second. 2.1 and carbon is about 2.5. So we're going to say that the difference in electronegativities, if hydrogen is about 2.1 and carbon is about 2.5. So the difference here is about 0.4, but we're going to say that this is great enough to be a polar bond. I know it's right on the border of what the textbook says, but let's just use this as an example. So let's look at methane. Let's look at carbon tetrahydride as an example. So here is the carbon tetrahydride molecule. Here's the Lewis structure. I have 4 plus 4 valence electrons. I have 8 valence electrons to distribute. This is the correct Lewis structure. Each of these is a polar bond. I know this is right on the border, but we're going to say that this is signifying a polar bond. So we would say the carbon-hydrogen bond, if we were to draw the dipole, remember the dipole is a vector that shows the separation of charge, we would show it pointing this way because carbon is more electronegative than hydrogen. So this would be considered a polar bond. It's right on the edge. But is carbon tetrahydride a polar molecule? So this is the Lewis structure. So from the Lewis structure, we would draw the molecular geometry. The molecular geometry would look like this. To the molecular geometry, we would assign what are called vectors or dipoles. Assign the vectors to the molecular geometry, not to the Lewis structure. Do not assign the vectors to the Lewis structure. So if we were to assign the vectors to the molecular geometry, we would do one for each bond, and then we're going to see what the sum of those vectors are. So for each of these bonds, the vector is going to be pointing towards the carbon because the carbon is more electronegative in each of these cases. Remember, this is not a flat molecule. This is a molecule in 3 dimensions, and I can post some good videos to show these molecules in 3 dimensions so you can see them rotate. Each of these angles is 109.5, and when you sum these angles together, they would all be equal and opposite. So these vectors are all equal, and the sum is 0. Because each of the magnitudes of these vectors is the same because it's the same magnitude of these 4 equal bonds, and the angles are all going to equal 0. So we would say this molecule has no net vector. Another way to say it is that there is no dipole moment. So this is a non-polar molecule. So the way that you determine if a molecule is polar or not is you assign vectors to each of the bonds in the molecule to the molecular geometry, see if they add up to something or see if they add up to nothing. So let's do one more example. Let's do water. So here my dihydrogen monoxide, to draw the Lewis structure, hydrogen is 1 times 2, oxygen is 6. I have 8 valence electrons. It looks like this. This is the Lewis structure. From the Lewis structure, we're going to assign the molecular geometry. The molecular geometry, remember we said this has a steric number of 4. So it has 2 regions of lone pairs and 2 regions of bonds. So the molecular geometry of water looks like this. It's bent. So now when I assign the vectors, oxygen is more electronegative than hydrogen. So the vectors would go like this. Pointing together, these are equal magnitude, but they are not opposite directions. These are not going to cancel each other out, which means the sum of these 2 vectors, molecular polarity is determined by summing all of the polarities. So this is like a physics thing. It's the angles. Do the angles cancel each other out or not? Here they do not. This would be the net vector of these 2 vectors when they're added together. So this does have, the sum is not 0. The sum is not 0. There is a net vector. there is a dipole moment. And this is a polar molecule. Water is polar because this molecule is bent and the sum of these vectors is not 0. If you were to have assigned the vectors to the Lewis structure, you would have thought that these vectors were equal in magnitude and opposite in direction. You would have thought that water was a nonpolar molecule, and that is false. So make sure that you are always assigning vectors to the molecular geometry. It doesn't matter what this net vector is, you should be able to draw it just like it's something in some direction. We're not going to be measuring what the actual quantity is, but you should be able to tell me, is there a net vector, yes or no? And if there is any net vector, then it is a polar molecule. It is not polar only if all the vectors are equal and opposite. Equal in magnitude, meaning all of these have the same magnitude bond. They're all carbons and hydrogens. If this was carbon and then this was chlorine and these three were hydrogen, then it would be polar because there's a different electronegativity between the carbon and the chlorine than there is between the carbons and the hydrogens. So it has to be different in magnitude, or it has to have an angle that's not going to cancel each other and not going to equal 0.